being like an addition. You're adding up those little volumes to get the entire total volume. That's an intuitive way to think about it. Once again, I emphasize that to actually do the integral, you want to integrate the constant function of 1. How can you think about that? Well, how does that make sense? Is there an analogy to this picture? Well, kind of. There is, but it would be all in your imagination, and you can't literally imagine it because it would be in 4-dimensional space. What's the graph of the constant function 1, quote unquote, above this solid? You can't think literally above because that's still in 3-dimensional space, so you have to imagine somehow there being a 4th dimension, and the graph of this constant function 1 is somehow above this 3-dimensional solid in some 4th dimension, and the triple integral really gives you some sort of 4-dimensional hypervolume. But because the hyper height is 1, you can find that hypervolume as the volume of that solid, the base, times the hyper height of 1. So you get the same answer, okay? Did you follow what I said there? Kind of confusing. You can't literally imagine it, of course, except in a pretend kind of way. But that is a way you can sort of think about it if you like. Okay? It's the 4-dimensional hypervolume under the constant function 1 in some 4th dimension that's also above that solid somehow. All right, some intuitive ways of thinking about it. No proofs there, just intuition. What are some other applications of integrals that we've talked about? We've mostly focused on this one. Finding the mass when you know a density, or finding the population when you know a population density. If you've got a lambda, a 2-dimensional thing, you can find the total mass by integrating the density. Again, intuitively, you think of this as being, well, this has got a density in units of mass per unit of area, for example, grams per square centimeter. You think of the dA as an infinitesimal area in, say, square centimeters, and you imagine this as being a product giving you a dm, a tiny little mass of that tiny little piece. And you've got to add up those tiny little masses to get the total mass. Works in 3 dimensions too, except the units would be different. Now the units of the density would be, say, grams per cubic centimeter. The volume there is in cubic centimeters. This is now your dm in grams. The integral again means add those up, add those dm's, those tiny infinitesimal masses up to get the total mass. The details of how to do the calculations, though, that's kind of challenging too. You've got some practice for today with these completion problems. I imagine it was pretty challenging to try to figure them out on your own. I would suggest continuing to practice them, going beyond what was assigned, practicing them some on your own. I'm going to show you some graphics that you can make in Mathematica that can help you think it through in the right kind of way in a little bit here. But it takes practice, whether you're doing it, maybe especially in rectangular coordinates, it's tougher because in cylindrical or spherical coordinates, we focus on the simpler shapes, like the cylinders and the spheres. These can also represent what are called, let's see. Okay, when rho here represents something called a probability density, and I will talk about this in a little bit as well, then the total mass ends up equaling 1, okay? And the reason you want the total mass of a probability density to equal 1 is that you want the probability of something happening in your experiment to equal 100%. Something is going to happen, okay? And effectively by rescaling things to make the total mass of the probability density, which again I'll talk about in a little bit, equal to 1, you're essentially creating a model in such a way that your probability of something happening based on your setup equaling 100% or 1 for the probability. Again, I'll talk more about that in a little bit here. Something else that's important to calculate with these integrals in physics involves centers of mass, and a special case of a center of mass called a centroid. And also, if you look at the book, there are calculations for things called moments of inertia. You're not going to have to know how to calculate moments of inertia. It would be worth looking at briefly to see some other applications. But as far as the test goes, you just need to be able to calculate, well, mass for sure, we've done that, center of mass, and centroid. And again, a centroid is a special case of the center of mass, which I'll talk about in a bit. Also, you should be able to do a couple basic examples with probability density functions that I was hinting at about a minute ago. How do you calculate centers of mass? Well, the first thing you need to do is you need to calculate things called moments. In the probability situation, moments correspond to means or averages when your density function represents what's called the probability density. In the actual mass situation from physics, then you're not thinking about probabilities, you're actually thinking about masses. And you do these calculations to calculate these things called moments. I'm not a physicist, and I'm not sure that in describing what these mean, I'm going to describe it as well as I can. But let me just give you a little intuition about perhaps how to interpret the meaning of these moments. Let's think about a two-dimensional example here. So you've got a lamina there, thin sheet of metal, sitting in a plane. But you're going to allow this thin sheet of metal to move into the third dimension here, something outside of the plane. In fact, you're going to imagine it may be attached with a thin rod of negligible mass to the y-axis here. And you might wonder, okay, if I give this a little push, maybe, what speed is it going to rotate at? What angular velocity might it have? Okay? And it turns out that the angular velocity is going to be related to the moment of this lamina with respect to the y-axis, which is labeled m sub y. It involves an x. That's not a typo. That's a y, that's an x. That's an x, that's a y. Okay? It should make some intuitive sense that the further this lamina is from the y-axis, the bigger the x-coordinates in the lamina are, the bigger the moment will be well, okay, maybe I'm going to say something wrong here. Maybe it's better to say it this way. For a given angular velocity, it's going to have more kinetic energy the further it is away it is from the y-axis, because it's going to be going faster. That's probably a better way to think about it. So the bigger the moment is, for a given angular velocity around the axis, you're going to have probably more kinetic energy for the lamina overall, based on a higher moment with respect to the y-axis. But for us, most of these are just stepping stones, unless you're in the probability density case, for calculating the center of mass down here. To calculate the center of mass for a two-dimensional lamina, you use these two formulas to calculate the two x and y coordinates of the center of mass. For the x center of mass, you take the moment with respect to the y-axis and divide by the total mass, which means doing these two integrals and then calculating their ratio. For the y-coordinate of the center of mass, ycm, you take the moment with respect to the x-axis, divide by the total mass. You calculate two integrals to get that ratio. That theoretically could take a very long time to do that calculation because you've got to do those two integrals. So on a test, there's things I could do to try to make things simpler for you, to make things more doable in a short amount of time. One way I could do that is I could make the density constant. Right, that would make these integrals on the bottom easier to calculate. Essentially, you just calculate the density times the area. And maybe I'd make the lamina a disk. Area equals pi r squared. Or a rectangle. Or a triangle, for that matter. That's one thing I can do to make the calculation simpler. Even if rho is a constant, the upper integrals would take some time to do. Maybe I'd only have you do one of them and not the other. There's sometimes where you can also use symmetry. If the density is constant, and if the lamina is, say, centered on the y-axis, maybe a triangle like this, isosceles triangle like that, then the moment of the x-coordinate of the center of mass, if the density is constant at least, is going to be 0. It's going to be on the y-axis, the point that is the center What's the application of a center of mass? Well, one application in a two-dimensional case is theoretically if you could somehow balance the lamina on a point of a pencil or something, you want the pencil to be at the center of mass to make it balance. Nobody can really do that perfectly, but get as close as you can. That's the idea. For a three-dimensional solid, you can't really balance on the center of mass because it's inside the solid, but one application is anytime you have a three-dimensional solid flying through the air, rotating in some strange way. Probably shouldn't have done that. I gotta erase the floor now. No, that's not good. That was probably a bad idea. Okay. What you want to do is you want to analyze the center of mass, the motion, by focusing on the center of mass. The center of mass, if you ignore air resistance is what's going to follow a parabolic action. That point at the location of the center of mass. Okay, so those are some basic applications of those. Centroid is the special case of the center of mass. When the density is constant, it's called a centroid. So the equations reduce, they become simpler. The notation is different too. X bar and Y bar are the coordinates of the centroid. Actually, I don't know why they don't maybe use the same notation for center of mass as well. They are kind of like an average. And in statistics, when you write an X bar, it means an average of a mean. What's happening here is the same formulas as before, except the rows cancel. The row in the other formulas is a function, but if that function is constant, it can be factored out in both the numerator and denominator, and then that constant can be canceled. So the integrals simplify, and again, you can think of the bottom integral now not as a mass, but as an actual area. So A is the area, and the three-dimensional case down here, the V is the volume. Once again, things can be made simpler with symmetry. You can just tell by the picture if X bar to Y bar is 0 based on the symmetry either with respect to the X or Y axes and the fact that you're assuming the density is constant. If the density is not constant, then you can't just look at the symmetry. You've actually got to do the integrals to get the answer. Now, what is this about probability densities? Again, you should read the book to get a fuller understanding of this. I'm just going to highlight the idea here and have mathematics do the calculations for me. I've actually had to do some already in the other class. Cut them out. What I'm imagining here is a situation where I'm doing some experiment where the outcome is some random quantity. For example, let's measure the temperature tomorrow at 10 o'clock in the morning. Okay? The value of the temperature outside at 10 o'clock in the morning is going to be some random quantity. I don't know exactly what it will be. I can give ballpark estimates based on knowing some meteorology and typical averages. A year ahead of time, you can't really look at the weather. You've got to just look at averages from the past to try to estimate what the temperature will be at 10 a.m. 1 year from today. Probability density functions try to model that kind of random experiment. And in this situation, you can imagine a random experiment where you've got two quantities that are random variables, and they vary jointly, maybe because of some kind of constraint in the experiment, between 1 and 4 along some triangle like this. Isosceles triangle again, making its corners at the points that you see there. So that is going to be the domain of the density function. Anytime I perform the random experiment and gather data about the values of x and y, the point x comma y has to be in this domain somewhere. That's the idea. I'm not saying what the application is. You know, this is just a completely made up thing. But that's the idea, and it does have applications. I'm not saying what the particular application of this function is. Now in the last class, I just made this function up here, x squared times y plus 2, without this number in front. Let me go ahead and cut that number out, actually. And I said, okay, let's let that be p of xy, and let's integrate that function over this domain here, this triangular domain, So take a look at this integral here. Because x is the outer one, I'm treating this as vertically simple. I could do it as horizontally simple too. If I treat it as vertically simple, x goes from 1 to 4. And for each x between 1 and 4, y goes from 1 up to the second coordinate of that point, which in terms of x is negative x plus 5. This line here is y equals negative x plus 5. So for a fixed x, that's the second coordinate of that point in terms of x. And that's the upper limit for the inner integral. When you don't have that factor that I cut out in front of it, the integral is not 1. It's 891 over 20. So this is not a probability density function as is. But you can make an appropriate adjustment to make it a probability density function. Whatever this integral happens to be, take that value and take its reciprocal. In this case, that would be 20 over 891, and make that the factor in front of the function, the original function we're trying. And now you will get a function that can represent a probability density function because of the fact that the total area under the graph is 1. Total volume, excuse me. Total volume under the graph is 1. Which again intuitively means that the chances of x and y being somewhere in the domain are 100%. 1 for the probability. 1 being equivalent to 100% chance. What are the applications of this? How do you now use this probability density function? You use it to figure out, for example, probabilities of being x and y being in certain other subregions, subdomains of this. For example, the application I have here, notice x is going between 2.5 and 3, and I have y going between the same values. So 2.5 is halfway between 1 and 4. And 3 is right about there. The subdomain I'm thinking about here is this trapezoid right here. I'm wondering, in this situation, what's the probability that my values of x and y form an ordered pair, a point that is in this region? And based on that calculation, the answer is about a 20% chance. The probability is about 0.2. That's what you use them for. One application. You can also use them to find means. And this is analogous to finding moments, actually. Notice you multiply this probability density function, the p, by x and y, and you get some other numbers. And these other numbers are telling you the mean for the x is about 2.3, the mean for the y's is close to 2. So that's saying if you perform the random experiment many, many times, over and over again, get lots of different values for x and y that all vary inside this triangle, that on average, the x's will have an average close to 2.3. Using the word average twice there. The average of the x's will be close to 2.3, and the average of the y's will be close to 2. That's the intuition behind what those numbers mean. Evidently, I mean, this has got symmetry with respect to the line y equals x. But on average, the x's are tending to be higher than the y's. You're tending to be over here more than you are over here because of the nature of the probability density function. I guess evidently because I squared the x, whereas I did not square the y. Okay. So some intuition there, you've got some reading on that, and you've got some problems, some creation problems related to that. All right, I want to spend a few minutes, not real long, just showing you a few cool things related to general change of variables and give you a recommendation as well. If you open up this section, I have the polar coordinate example from before here, but I also added in my solution to exercise 25 in section 15.6. What's the reason I put this in here? The reason I put this in here is because it's a non-trivial example that we haven't done in class. What we have done in class are polar coordinate examples and the example with a parallelogram. This example is not a parallelogram. It's another shape. I'll work the cut out the picture I was wanting to see. Well, we can look at this one anyway. Got to plug this function in. The domain, after the change of variables, you ultimately integrate over this square down here. But before the change of variables, the domain in the xy plane looks like that. And that is not a parallelogram or a disk or a washer or anything like that. It's some other shape. And therefore this would be a harder problem in general. You won't have one this difficult on the exam, but I would suggest that you read over the solution, especially if you skip this problem for your completion assignment. You read over this description of the answer and how to find the value. Notice the Jacobian is not constant. The Jacobian determinant is 2u over v, so it's its absolute value, and u are positive, which they are. So that's a non-trivial example. The integral actually ends up being pretty nice. Not too hard to do there. We're trying to find the area of the region, so the function's pretty nice, just integrating 1. It's kind of a cool problem, and if you study it, even though we're not going to have one that hard on the exam, I think it is enlightening, helps you understand what's going on better. And you do also see here in the animation how the mapping stretches some areas and maybe shrinks some other ones. It looks like it's mostly stretching here. The absolute value of the Jacobian is 2u over v, so what that's telling you is it's especially stretching regions where u is large and v is small. The lower right corner points get stretched, so to speak, more than the upper left corner points do. These are the points where u is higher and v is lower, so that this fraction is higher. So it's those lower right corner points that get stretched the most. The areas get magnified the highest near points in the lower right corner under the transformation. Again, the intermediate pictures are just for fun. They're not really what's going on in a technical sense, but it's fun to imagine it this way, and many mathematicians do imagine it this way, as a visual way to see the stretching going on. I also want to encourage you to open up this section and experiment with it. It's about something called conformal mappings, and there's a Wikipedia page on conformal maps. You can donate to Wikipedia if you like. Conformal maps are really interesting. They are a big part of a subject called complex analysis, which is about complex numbers. And one important thing about conformal maps is they preserve angles. That's essentially the definition of a conformal map, is it preserves angles. So you get grids like this getting mapped to stretched and rotated grids like this in some odd way. But what happens is, since these angles were 90 degrees, these curves are intersecting at 90 degree angles as well. If you look at the angle between their tangent lines when they cross, the angle between the tangent lines will be 90 degrees. I've got lots of examples in here that you can experiment with, take a look at. This one's kind of interesting. I've got an animation of that one as well that it's kind of hard to understand what's going on. It's kind of like the plane is turning inside out somehow. Okay? If you want to understand that better, then I have another suggestion for you. A friend of mine, Jonathan Rognes at the University of Minnesota, along with somebody else, I think it was Doug Arnold, has made a video, I think about 7 or 8 years ago he made this, called Möbius Transformations Revealed. And I'm not going to take the time to watch it in class here today, but you can see you've got interesting looking pictures like this related to conformal
The true
maps.
unity of Möbius transformation
And it brings it into the third dimension as well, so it's pretty cool. Take the time to look at that. I strongly suggest it's pretty interesting, and it helps you understand in another way why the maps do what they do. Okay, so that's supposed to be just encouragement to explore. All right, for the last 18 minutes, what do we have here? I want to focus on starting the next chapter. I'll focus on what are called vector fields. This is not going to be our very last chapter of the class, actually. In this chapter, chapter 16, we're going to do 3 sections, 16.1, 16.2, and 16.3. Then we're going to skip ahead and do 1 section of chapter 17, on something called Green's theorem. And I hope I have a green tie by then that I can wear to talk about Green's theorem. What is it about? Well, vector fields have lots of applications. One application the book hints at is fluid flow. The fluid can be a liquid like water. It can be the air, which has got lots of different atoms in it, molecules. But what you imagine when you're modeling fluid flow is you don't really think too much about the molecules themselves. Instead, you sort of imagine the fluid in chunks, like the waters, like streams of water moving in chunks. And vector fields can be used to model it. That's one application. Another application that we'll talk about is vector fields can be used to model what are called force fields, like gravitational fields, for example, and electric fields. And based on Newton's laws, you can then use the vector fields to figure out what the motion of a mass would be in a gravitational field, or a charged particle would be in an electric field. So that's a little hint about what the applications are. We've talked about vector fields before already, because we talked about gradients of functions. For example, take a simple function like x squared plus y. The gradient of that function is a vector field. You can think of it as a function. I haven't typically put the x comma y there before, but I'm doing it now. The components are the partial derivatives, which in this case are going to be 2x and 1. And that's a function. That's a function that takes a two-dimensional point as input and gives you a two-dimensional vector as output. And you can plot it. Remember what we did? For example, if I want to plot this at the point 2, 3, what do? We did do this. Not real. Didn't spend a ton of time on it. What should I do? How do you plot this? What am I talking about? Or take a guess. I can't remember what what's the answer. No?
You plug the point into the gradient vector and use that as the vector from that point.
Yep. And you plot the vector to be based at the point. Yeah. So this is the point 2, 3. What's the gradient vector at the point 2, 3? Plug it into the formula. Get 2 times 2 is 4 for the first component. The 3 is irrelevant. The second component of the vector field is 1. Always, no matter what point in that. So it's always going to have vertical displacement of 1. It will be a point like this or like that. The horizontal displacement will depend on x. If x is positive, it'll point to the right. And if x is negative, it'll point to the left. At the point 2, 3, it's the vector 4, 1. So if I'm going to plot this vector accurately, I want to plot it about like that. Point 2, 3 is the input, and the vector 4, 1 is the output. Also, the further x gets away from 0 in this vector field, the longer the vector is going to be, because 2x will get further and further from 0. To plot this by hand, you got to plot it at a bunch of points. Theoretically, you can plot it at any point. So you can't make the entire plot, because that would be infinitely many points and vectors to plot. But we plot some of them on a grid. And Mathematica can do this with vector plot. And just this part here is enough to make the plot. Like that. The vectors are not accurate, they're too short, because it makes for a nicer picture when you scale them all down by a constant factor. I'm assuming that proportionally speaking, it's hopefully accurate. That, for example, How much longer is this distance compared to that one? I don't know. 5 to 10 times longer. If you pretend it's 5 times longer, then the constant factor you're scaling the vectors down by is 1/5. I hope that's the case. I don't actually know for sure. But again, ultimately, the vertical displacement of all these vectors is constant. It's always 1. It's the horizontal displacement that changes, either positive when x is positive or negative when x is negative. When x is 0, when you're on the y-axis, all the vectors point straight up. They're all j-hat, really. 0, 1. This example. This is the gradient vector field for the function x squared plus y. So if I combine this with contour plot, get rid of this for the moment, with show, I can see that those gradient vectors are perpendicular to the level curves wherever they are based. This one is based right there on this level curve. It is perpendicular. So in other words, orthogonal and normal are other words that are used to the level curve at that point. Points from dark to light, decreasing to increasing, well, in the direction of increasing values of the function. In fact, in the direction of fastest increase at that point. Reviewing directional derivatives, like in the last exam, if you wanted to maximize the directional derivative, what direction should you pick for your unit vector u? You should pick the same direction as the gradient vector at that point. That was on the last exam that I put in the POs yesterday. And also, if you wanted the value of that maximized directional derivative, it would be the length of the gradient vector at that point, which again is longer than this. Some length about like that is going to be the value of the directional derivative of the function at this point. The vectors are longer when the level curves are closer together and shorter when they're further apart. For a constant contour interval where the outputs of the function keep increasing by the same amount when you draw the level curves. And Mathematica picked it here in this case to make this level curve be at 0, and then it keeps going up by 0.47. Moving up. The value keeps going up by 0.47. That's the contour interval in the book's terminology for this particular contour map. Let me put it back in here what I cut out here initially. Oh, I can't find my comments too good. Is that a comment? There we go. Okay. What's this? Stream plot. What's that going to be? Take a guess. I'm making it blue. It's going to make stream lines? Yes, it does. The red arrows are straight, they are vectors. These blue arrows are not straight, they're technically not vectors. Well, I guess these are straight. Don't think of them as vectors, think of them as streamlines, think of them as paths that water molecules would take. If the vector field was a velocity vector field for the water molecules. Imagine this is a thin sheet of water now. Not metal, but a thin sheet of water, a thin fluid. How could you do that? You could, put two metal plates close together and have the water go in between them. So thin that it's like one water molecule deep or something. That's probably not possible, but pretend it's possible, and pretend that again the red vectors are velocity vectors for the water molecules, meaning anytime a water molecule passes through the base of one of these vectors, that vector represents the velocity vector for the water molecule at that point, and at that moment in time. That's going to mean that the water molecules are going to follow these streamlines. That's what the stream plot is showing. How do you find the streamlines? Well, technically speaking, you need to use differential equations. You need to use ND solve or D solve or solve it by hand to find formulas for those curves as actually parametric curves that will follow the vector field anytime they pass through one of these vectors at that given point. That will be a velocity vector for that particular parametric curve, that particular water molecule at that particular moment in time. When you think about this initially, you don't want to think about too much about the physics. You're just imagining. You don't want to worry about the fact of, can water molecules really do this? I mean, one thing that's with me about the water molecules is, since these vectors are getting longer and longer, they're going faster and faster. Can that really happen? Probably not. I don't know. Don't think too realistically about what's going on. I mean, another thing that's going on is if they go out far enough, these vectors are going to get longer than the speed of light, and the water molecules are going to be going faster than the speed of light. Can't happen in the real world. But in the pretend world of imaginary mathematics, when I say imaginary, I mean in your imagination. You're imagining this to represent the water molecules as a hint of the possible applications. In that imaginary world, then things can go faster than the speed of light, and everything, I guess, is Newtonian instead of having to worry about relativity. In a fluid mechanics class, like Professor Keith Stein teaches here, you would learn more about what makes a realistic flow. What kind of vector fields are going to give you realistic flows of fluids. But in this class, we don't worry about it. We just use our imaginations and pretend. And we don't worry about the realism of physics. Math is less constrained than the physics. We're not worried about real life. There are lots of other vector fields you can make. This one's pretty simple. F of xy equals x normal y. I'm not writing a little f here. I'm not saying this is the gradient of some function yet. And in the absence of a little f, it's traditional to call this capital F, and when you write it by hand, put a little vector symbol above it in the book to make it bold-faced. Pretty simple formula in this case, f of xy equals xy. Take a few seconds to try to imagine what you think the graph of this one looks like. You can actually graph this by hand pretty quickly if you think about it in the right way. All the vectors point directly, finish my sentence, away from the origin. And technically, if they're not shortened in length, their length is equal to the position vector length at the given point. So if you're at this point and you want to draw accurately the vector and the vector field at that point, it is in this direction, straight away from the origin, and its length would be the same as the length of the position vector from the origin to that point. In fact, you could take the position vector from the origin to that point and translate it up there, and you get the correct vector for the vector field. And it's got to be that way because of the formula. The formula is the output vector has the same length as the distance of the original point to the origin, and it's got to point along the same ray away from the origin. Actually, for this example, when you encounter this kind of example in differential equations, which you will, the vector field at the origin is the zero vector. And it is important, especially in differential equations, to make a dot at the location of spots where the vector field has an output that's the zero vector. That's important in differential equations. You got to put those points in there. They're called equilibrium points, and they help you understand what's going on. And as far as the applications go, you can imagine, I suppose, this is like being a fountain. Water is bubbling up out of the fountain and moving away from the fountain, although it's speeding up as it moves away. And that justifies calling this a source. This is often called a source for this vector field. There are sinks too, and saddle points as well. This is a gradient of a function, and it's pretty easy to figure out what function it's the gradient of. What function of two variables x and y can you create that's going to have a partial with respect to x that equals x and a partial with respect to y that equals y? Well, x squared over 2 plus y squared over 2 certainly works. Or I could add a constant to that. In fact, that's kind of like, I sort of took an antiderivative, didn't I? That's a function whose gradient is the original vector field. In such a situation, there's some terminology that's a little strange for a math course, but it comes about because of physics. In such a situation, the vector field is called a conservative vector field, and this function is called a potential function. Potential function, because it is typically related to potential energy, and conservative vector field because it is conservative in the physics sense of conserving energy. Now, actually, energy is conserved in all systems, but with conservative vector field, you say that mechanical energy is conserved as well, not just, well, then that's the only kind of energy you really think about. That mechanical energy coming from motion, that's both kinetic energy plus potential energy. So, conservative vector fields are ones that have potential functions. They're very special. If you just sort of write down an arbitrary vector field, most likely it's not going to be conservative. For example, this is the one I typed out in the last class right here. F of xy equals x squared times y, comma, y cubed plus x times cosine of y. In all likelihood, that's not conservative. That's not the gradient of some potential function. There is no potential function in all likelihood unless I chose very unluckily. Should I say lucky or unlucky? There's what its graph looks like. Before I put this on Moodle, I think I'll add the stream plot. And I think I will also confirm, based on things you'll read about in section 16.1, that this vector field, in all likelihood, is not conservative and does not have a potential function. Though, if somehow it does, I will be amazed. Okay? It was a randomly chosen vector field. Pseudo-random. All right? So that's what to expect. You should make sure you download this off of Moodle and look through the things I told you to look through. On Friday, we will also do an example of a triple integral, do a calculation by hand. The key thing being identifying a solid, for example, as being vertically simple. Okay, we'll talk about that on Friday.